All right, howdy class. We've begun our descent into a discussion of phase transitions. And last time we noted a couple basic features of phase diagrams and how much information they contain. Today we're going to continue a discussion of the thermodynamics of phase transitions and really focus on some of the struggles that thermodynamics has in understanding and coping with the existence of phase transitions. In that we'll talk specifically about a couple paradoxes that result when you start thinking about phase transitions that seemingly seem inconsistent with both thermodynamics and a naive perspective on statistical mechanics. And we'll start patching that up. We'll start seeing how exactly statistical mechanics comes in to save the day, and how there's a simplicity associated with phase transitions that makes tackling them tractable in a way that at first blush may seem really difficult. Specifically, we'll find that in order for a system to undergo a phase transition, there must be interactions. Interactions make our life a lot harder in computing things like partition functions. Nevertheless, the existence of something called universality will offer some simplifications and make studying them tractable, studying phase transitions tractable. All right, so that's where we're going. That will lead into next week a discussion about simple models we can use to study phase transitions. But before we get there, let's review what we talked about last week. So last week we reminded ourselves of some basic statements that thermodynamics requires if we are to see the coexistence between two phases. So at coexistence between phases, say alpha and gamma. So the picture we should have in our mind is we have some box, we have some alpha phase in contact with some gamma phase. This could be, for example, water and air. It could alternatively be water and oil. There are two phases that are in coexistence with each other. It must be the case for the equilibrium of that state to be well defined that the temperature of phase alpha be equal to the temperature of phase gamma. Otherwise, energy would flow from alpha to gamma. It must also be the case that the pressures are the same. And finally, that the chemical potentials are the same. If there are many components in those two phases, the sharp statement we have to make is that the chemical potential of each component in each phase is equal. So if I have a mixture of water and oil, for example, there's going to be some amount of water in the oil and some amount of oil in the water. The chemical potential of the oil in the water must be equal to the chemical potential of the oil in the oil. And analogously, the water chemical potential in its majority component must be equal to the water in the oil when it's in the minority component. Those basic constraints give rise to the so-called Gibbs phase rule. A so-called, it's essentially just accounting for the constraints that we have to satisfy above and the different control parameters we have. So what can vary in two phases, or some number of phases, we found that the number of independent parameters, call that F, was given by 2 plus the number of components I have minus the number of phases that are at coexistence. So for a single component system, I can have a single phase, in which case I have two independent parameters. That's like saying that I can move around both in the temperature and the pressure. I can move both of those independently and stay in that one phase region. However, if I have two phases, so I'm at coexistence between two phases, like the liquid and the vapor, in a one component system, I only have 1 degree of freedom. So I can change the temperature, but if I change the temperature, I have to analogously change the pressure to stay on that coexistence line. Having multiple components makes this incredibly difficult to think about constructing phase diagrams. Nevertheless, if we only vary the temperature, pressure, and compositions, Gibbs tells us what sorts of phase transitions or phase diagrams are possible. Indeed, if we were to measure a coexistence curve, for example, in the pressure temperature plane, say for phase gamma or phase alpha. That's a terrible alpha. Let's try that again. We also arrived at a condition that has to be satisfied along that line, because not only does the chemical potential of both phases have to be the same at a point on that line, but to move along that line means that the changes in the chemical potentials of both phases have to be the same. Invoking the Gibbs-Duhem equation, let us write down that along that line, so the slope in the temperature and pressure plane along coexistence actually gave us information about, for example, how the entropy changes in going between those phases relative to how the volume changes between going between phases alpha and gamma. Again, these little s's are the entropy per particle, and these little v's are the volumes per particle. This is the so-called Clausius-Clapeyron equation, which could be used to extract the ratio of the change in the entropy to change in volume by noting the coexistence line, or it enables us to predict the slope of that line by knowing the ratio of the change in the entropy to the change in volume. Finally, provided an equation of state, we can use thermodynamics to establish where coexistence might occur. We saw that, for example, in the van der Waals equation, a state noting instabilities, one could imagine that maybe those instabilities were real and thus invoke coexistence to patch them up, giving rise to a Maxwell construction. That's kind of an ad hoc fix, but in general, if we had how the free energy varied as a function of, say, the volume of the system, we can use the basic statements of equality of chemical potentials, pressures, and temperatures to deduce where the phase transition happens and where coexistence must set in. Okay, so that's all stuff we talked about last week. I want to now have a discussion about some of the difficulties that thermodynamics has in thinking through or working with phase transitions. So I want to state a few empirical observations, things that I like to think of as paradoxes that thermodynamics has. Okay, let's start with the first. Let's consider a system for which we control the pressure and we measure the volume. All right, so we might, for example, consider doing such an experiment with a vapor. Now we know that if we increase the pressure, the volume has to go down. Indeed, vapors are reasonably compressible. Most vapors, if we were doing this experiment at ambient conditions, there's a little picture of a vapor, would get to a point whereby if we compressed any further, rather than seeing a smooth change in the volume, we would see a discontinuous change. That discontinuous change would happen at a very precise pressure, called the coexistence pressure, and would result in the condensation of that vapor into a liquid. We could label how big of a change of volume took place, some delta V, which is in general quite large. So in doing this experiment where we measure V and control P, we observe an abrupt change in the volume, exactly at a very exact pressure, thermodynamically speaking. One could ask, for example, how sharp that change is. So dV over dP is a measure of that sharpness. In the limit that both of those are small, that's dV dP. Exactly at coexistence, that is infinity. I get a finite change in the volume, delta V, over an infinitesimal change in the pressure. 1 over a really small number is an infinitely large number, or 1 over an infinitely small number is an infinitely big number. How can that be? How can we get an infinitely sharp change? This is, I think, so commonplace to us all. We all the time see examples of sharp behavior when we consider phase transitions, but it is a really odd thing to have happen. If we, for example, considered P underscore lick to be the probability of observing the liquid state, that probability could be computed from grouping all of the microstates associated with the liquid over all the total microstates in a system. For example, in a canonical ensemble, summing up all those microstates times their Boltzmann factors. That sum could be written as an integral. It's an integral over all the positions, where we only include those configurations where we are in that liquid state, and we're summing up those Boltzmann factors. We know that we only have to do this for the positional part because the momentum part is trivial. Now, this function, Q, as is the total Q, is a sum. It's a sum over microstates. Those exponentials that you sum over are smooth functions. Away from t equals 0, an exponential is a smooth function, infinitely differentiable. If I take a sum of smooth functions, I necessarily get a smooth function back out. Even if there's a, so a sum of, so a exponential is a smooth function. If I take a sum, even integrating, so I have a lot of smooth functions, I still get back a smooth function, and yet Q, for us to observe a sharp transition, has to have a singularity in it. So how can that be? How can we get a singular change from a smooth function? We could have equal as plotting the volume as a function of pressure, plotted the energy as a function of temperature. That too, when I go from the liquid to the vapor, would exhibit a sharp change. And yet we know if we can compute Q, the partition function, we can take a derivative with respect to beta and get the average energy. If that function is smooth, taking a derivative returns another smooth function. That's what it means to be smooth. The energy would therefore not have a singular change. So what's going on? How can we reconcile this? Empirically, it is certainly the case that there are abrupt changes, and yet it would seem that our partition function, the way we compute that partition function, is inconsistent with that singular response. All right, that's paradox number 1. Number 2, let's consider a very similar sounding experiment. Let's consider controlling the volume and measuring the pressure. We can carve out different size boxes to put the same amount of stuff in that box. pressure is something mechanical, just a force on the wall. We can measure that, nothing wrong in principle with this sort of thought experiment. So measuring P as a function of V. So again, if we started in the vapor, that's a high volume, low pressure state. If I started trying to fill more and more stuff in that volume or shrink that volume, the pressure will rise. Eventually, if I shrink the volume enough, we'll see condensation. If I take the liquid that condenses and compress it even more, the pressure will continue to increase. So we go from a vapor to a liquid. But now if I'm controlling the volume, if I set up a volume that was intermediate between the liquid and the vapor, say this volume here, if I'm controlling that, I can set up that volume. I can measure the pressure. It would fall along this line. But not only that, I could go in and look at what that system looks like. And it would show that it's at coexistence. I have some amount of liquid and some amount of vapor. All right, this all seems relatively straightforward until we recognize that by doing this experiment, controlling the volume and measuring the pressure, we have accessed a state, this coexistence state, which we could not access in the other experiment. So if we went back up here, by controlling the pressure, I hop immediately from the vapor to the liquid. I never can stay right in between. And because that is infinitely sharp, an infinitesimal change in the pressure off of that coexistence pressure will dump me into either the liquid or the vapor. I can never find a pressure, I can never control the pressure precise enough to actually see something in between. That is paradoxical. That tells us that the macroscopic state of the system depends on whether we control the pressure or the volume. That should make you all very uncomfortable. A lot of the thermodynamic results we've derived assume that we can go in between ensembles or go in between representations of our auxiliary functions, go in between the Gibbs free energy description of the system or the first law description of the system and not lose any information. And yet this is telling us directly that if we control the pressure or we control the volume, we see very different macroscopic results. It's like saying that the NPT ensemble and the NVT ensemble are not equivalent. Ruh-roh. Sounds dangerous. All right, that's number 2. Let's list one more. The compressibility, kappa of T, is defined as 1 over the volume dV dP at constant T with a minus sign. So that is the volume change per pressure change by dividing by the volume, we've made this thing intensive. So the volume is an extensive quantity. The pressure is an intensive quantity. I have volume, differential volume over total volume. That should render kappa of T intensive. We have previously shown that this whole quantity is proportional to the fluctuations in the volume over the average volume. Yet if we were to plot this as a function of pressure in this experiment that we just did, so controlling the pressure, that's the first experiment. So differential change in the volume as a function of the pressure, that's going to give me one slope at low pressure and another slope at high pressure. But exactly at this coexistence pressure, that discontinuity means that kappa diverges. So kappa goes to infinity at the coexistence pressure. That means that fluctuations become infinitely big. Because kappa of T is just proportional to the fluctuations in the volume. For that to diverge must mean that that numerator gets infinitely big. Volume, of course, stays some finite value, doesn't go to infinitely small. So the only way for that to diverge is if the fluctuations get infinitely big. This is our third paradox. How could it be that fluctuations get infinitely big? Where does the infinity come from here? So what can we do to reconcile all of these observations? All right, well, let's start with the first, the existence of a singular response. So there is one loophole in what I told you. Q is a sum of smooth functions. It can, in fact, be singular only if the number of terms in that sum is infinite. So if I have an infinite sum of smooth functions, that can itself become non-smooth or singular. Now, in the past, we've divided up our space into M uncorrelated regions. We've often drawn our space as existing on some grid, like so, let's, for example, imagine that, I can use a color. Some of those grid points are liquid-like. The ones that are empty have a low density, those are vapor-like. So these ones here are cells that have a microstate in that cell that looks like it's liquid. These cells here have a microstate that looks like it's vapor. Now let Q cell be the partition function for each cell. That cell is finite in extent. So Q cell is some finite number. Which means that even though it's a finite sum of smooth functions. There's a finite number of microstates in any finite size cell. So this must be a smooth function. If we can grid up space into M uncorrelated regions, that would mean that our partition function has some form little q cell to the M, which means that minus beta A, which is always log of Q, in this case being minus M log Q cell. That means that A over M is a smooth function. So there's not a trivial reason just by having a very large system that we could get a singular partition function. Even if the system is itself macroscopic in extent, if we can divide up space into uncorrelated regions, just taking the system to be large doesn't result in a singular response or a non-smooth function. So to reiterate, if A over M is smooth, because even if I take M to be large, A also being extensive will grow. A over M, this becomes a finite number, which itself is smooth. And if A is smooth, we know that the volume is related to A, or the pressure is related to A by some derivative with respect to its conjugate variable, P or V, depending on whether A is the Helmholtz free energy or Gibbs free energy. If A is smooth, therefore, there is no phase transition. There's no way to have a singular response. That tells us immediately, actually, that this gridding up of space must be to blame. It must be the case that we cannot divide up space into uncorrelated regions. Another way of saying that is that phase transitions correlate molecules over macroscopic scales. to reiterate, even if those regions, these little boxes we've gridded our space up into, even if they're macroscopic, they would have a finite number of states in them. And thus, Q, little q, Q of the cell, even if it's macroscopic, so that I can do that counting independent of the counting in the neighboring cells, if that little q is finite, even if I take the number of cells to be very big, I will get a smooth function back out. So it is only then possible to get a non-smooth partition function if I cannot break up my system into these independent regions, if I can actually take the number of terms in my sum to be infinitely large. This observation, that lacking our ability to carve up space into uncorrelated regions, independent regions, necessarily means that those correlations therefore exist over macroscopic scales, informs the second paradox, the difference between controlling P and measuring V, or controlling V and measuring P, which is that ensemble equivalence depends on Legendre or Laplace transforms. That's how we've proved it. So we derived auxiliary functions to allow us to control the temperature instead of the entropy, for example, through a Legendre transform. We noticed that the microcanonical and canonical partition functions were related through a Laplace transform. The equivalency of those two descriptions, and thus the transformation that lets you go between the two, are invertible only for smooth functions. For example, controlling temperature, pressure, and number of particles as I would with the Gibbs free energy is related to controlling the temperature, volume, and number of particles as I would through the Helmholtz free energy. They are related through a Legendre transform, which depends on how the Helmholtz free energy changes with volume at constant T and N times the volume. If A is not a smooth function with V, this is not invertible. I can't move that derivative. I can't divide through by that derivative. I can't move. If I have an infinity over on the right, it doesn't even make sense to construct the left-hand side. All right. What about that last observation? So we've understood what is required to get singular responses. We now understand why it's possible to have ensemble inequivalence. How is it possible we get a system that has divergent fluctuations? Let's, for example, imagine computing the volume as a sum over little volume elements. So let's imagine that each one of those little cells, we can break up our system into cells. that are V in size, and there's M of them, such that the volume, total volume, is the sum of little fluctuating volumes. And let's not assume that those volumes are independent. They may be correlated. The fluctuations of the first volume may depend on what the second volume is doing. Well, the average volume in the system is just going to be M if all the cells are statistically the same. The average volume in the system, the average of a sum is the sum of the average. So the average volume is some extensive quantity that goes like the number of cells times the typical volume that each cell might have. The fluctuations in the total volume is equal to a sum over I and j from 1 to m, the average of vi, vj, less that average of vi, average of vj. That's just introducing v as a sum, squaring it, and subtracting out its average squared. That sum has how many terms? Well, I runs from 1 to m, and j runs from 1 to m. So there are m squared terms. So if I look at the quantity fluctuations in V over average V, if those VIs and VJs are correlated such that I can't independently average VI from VJ, there is going to be an order M size to that ratio of fluctuations to the average volume. If and only if all of those cells are correlated. Such that I really do have m squared non-zero terms. If I take m to infinity, that ratio of the fluctuations to the volume is going to go to infinity. So what have we just shown? We've just shown that we noted earlier that the compressibility, how the volume changes with respect to pressure, is proportional to the volume fluctuations over the average volume if I have correlations over the full size of my system, such that I keep all m squared terms in the equation for the variance of the volume, and I take the number of those terms to be infinity, such that I have an infinitely sized system, I indeed will find that those fluctuations grow unbounded. So the combination of long-range correlations such that all of the terms in the sum are non-zero, and the thermodynamic limit in, or in this case M, gets really large, gives rise jointly to a diverging fluctuations, gives rise to diverging fluctuations, and therefore to diverging response, because fluctuations are always proportional to response. So this is where the difficulty comes in. If we have to have correlations to see singular responses or phase transitions, it won't work for us to study non-interacting models. We need to consider models which have explicit correlations. Which in general is hard. That's a bummer. Studying interacting models, we can't factorize our partition function anymore. We won't, in general, be able to compute it in a simple way. And yet there are glimmers of hope. Those come in the form of what is known as universality, and the concept of symmetry. Okay, so let's illustrate those two concepts through an example. Let's consider again liquid-vapor coexistence. So if I was to measure the density as a function of the temperature at coexistence, there would be a high density state and a low density state. If I kept the system at coexistence and measured the liquid density, it would decrease. If I measured the density of the vapor along coexistence, it would increase, and both would merge at a point. Let's call that point Tc in temperature and rho c in density. So again, this is the coexistence curve. If I set the system up with a temperature and density under that line, I would see the system phase separate into a liquid in contact with a vapor. Now this point near Tc and rho c is special. In fact, if I was to measure the density, less that its C stands for critical, near its critical density, we would find that it behaves as a power law relative to Tc, the critical temperature, where that power law has an exponent beta. Now that's not Boltzmann's beta, not kBt, rather a number 0.32, to which you say, well, for what liquid and what vapor? This turns out to be the number independent of what the fluid is. Could be water turning into water vapor, could be methanol, could be argon liquid evaporating into its vapor. If I measure near their critical densities and temperatures, I find a scaling for how the density of the liquid branch or the vapor branch relative to its critical density changes with temperature. There are in fact very few exceptions for the scaling. One has to be pretty exotic, look at very heavy molecular weight polymers for you to see deviations in this number. By and large, this exponent is universal. It doesn't depend on the details of the fluid that you're doing this measurement on. Okay, that by itself is rather interesting. It tells us that independent of the details, a quantity, how the density changes with respect to temperature, is universal. Let's consider a different phase transition. Let's consider a binary mixture. Say of two fluids, and let's plot the temperature versus composition. For concreteness, let's imagine an oil-water mixture. So at low temperature, if I put water in contact with many oils, let's call X high, meaning mostly water, X low being mostly oil. There is some amount of water in oil. If I put, say I take some olive oil in my kitchen and I put some water on top of it, there will be some amount of oil soluble in the water and some amount of water soluble in the oil. And you all probably have the intuition that if I increase the temperature, I will increase the amount of water soluble in the oil, and I will increase the amount of oil soluble in the water. In fact, if you increased it enough, there's a temperature at which the two become miscible. So if I set the system up with a composition and temperature below some Tc, I would find coexistence. I would find water sitting on top of oil. If I look really close to Tc and measured how the composition changes relative to its critical composition, I find a power law. Depends on the distance of the temperature from Tc. And the exponent of that power law is 0.32. 0.32, did I just make a mistake? That's the same as the power law we just found for liquid vapor coexistence. Are you sure? I am sure. And in fact, not only is it the same for water and oil, or an oily phase in contact with a watery phase, but it is the same for many, many, many different mixtures. I take any two components that can undergo a so-called miscibility transition, a transition by which I increase the temperature and I go from an immiscible mixture to a miscible mixture. I will find the exact same power law behavior. All right, that's kind of interesting, but you could say, well, those are just two different sorts of fluid transitions, to which I would say, well, actually it turns out that if I had a solid solution, works the same way. So I dope in some amount of, say I have silver iodide. If I dope in some amount of bromide at low temperature, the bromide will phase separate, forming little clusters. If I increase the temperature, it will undergo a miscibility transition where the bromides and iodides are equally distributed through the lattice. All right, but most shocking, I think, is if we were to consider a magnet. So pull out your fidget spinners and let's measure the net magnetization of that magnet. Let's imagine this is an easy axis magnet, so it either has a magnetic moment pointing up or pointing down. If I was to measure that magnetization, it's a function of temperature. If it was pointing up, if I increase the temperature, I would find that magnetization would go down, eventually going to 0. So let's consider a bar magnet. One end painted red, the other end painted white. Let's imagine it was pointed up like that. If I increase the temperature of that magnet, throw it in a microwave, I could demagnetize it. Turns out if I cooled it back down, it could very easily change sign. It could generate a magnetic moment that was now pointing down from the white side to the red side. It could just as easily go back to where it came from, but in fact it could actually go either way. If I was to measure exactly how that magnetization changed as I approach Tc, the temperature at which the magnetization goes to 0, I would find that it acts like a power law in temperature away from Tc with an exponent of 0.32. And that is the same for many, many, many different magnets. Now, this is really surprising. Not only is there a universal exponent that tells me how the density varies as I approach a critical temperature for a liquid vapor transition. Not only is there the same exponent that tells me how the composition changes as I take a mixture and heat it up, but if I take something that really does seem completely unrelated to the two, like a magnet, and ask how does the magnetization change as I increase the temperature, I get the exact same exponent to empirical accuracy. And these numbers have been measured much further than 2 significant digits. I just don't remember them. That is the concept of universality. Universality is the notion that seemingly disparate phenomena like magnetization or liquid vapor transitions have some underlying connection, some universal behavior that tie them together. Beta is something we call a critical exponent. That is the power law, codifies the power law relationship between temperature and rho, x, or m are all examples of what we call order parameters. Those are numbers that distinguish two phases. So the density, if I'm below Tc, if I set the system up at a density, I uniquely know if it's a liquid or a vapor, because that's really what I mean as the distinction, is what its density is. The composition, whether it's watery or oily, specifies which one of those phases I'm in, if I put those two in contact with each other. These notions can be generalized, so similarly, if I was to measure the heat capacity, which is nothing but how the energy changes with temperature, say at constant volume and number of particles, as a function of temperature, for any of those transitions, liquid vapor transitions, demagnetization transitions, miscibility transitions, if I measured the heat capacity near that critical temperature, what I would find is that the fluctuations diverge, and thus so does the heat capacity. And near Tc, that divergence goes like T minus Tc to the alpha, where that alpha is the exact same number for all of those transitions, being something a little greater than a tenth. I could measure kappa, a generalized susceptibility, could be the compressibility in a liquid vapor transition, could be how the magnetization changes with applied magnetic field. If I was to measure it as a function of temperature near Tc, well, we've already discussed how the compressibility diverges. If I measured it, we would find that close to Tc, it scales like a power law with a exponent minus gamma, where gamma independent of it being a liquid vapor transition or a magnetization transition is 1.2. So the susceptibility is how the order parameter, let's not use kappa, let's use some chi function. So just for completeness, chi is how the order parameter like the density or the composition or the magnetization, how it changes with its conjugate field. Which could be, for example, how the density changes with pressure, or how the magnetization changes with some applied magnetic field. Irrespective of what that susceptibility is, if I measured it, I would find that universality, that commonality of the dependence of that function on temperature with a shared universal exponent. So now we're really in a position to define this on the page. Universality is the commonality despite molecular distinctions. Okay, so that's universality. There's another notion which is similarly important and simplifies our notion of phase transitions, which is that of symmetry. Now again, let me illustrate symmetry by example. And I'll consider this time the case of a magnet, where the symmetry is the simplest to see. So let's consider a magnet. Indeed, redrawing that bar magnet we imagined before, some north-south poles, some magnetic moment pointing up, say in the z direction. Bar magnets typically colored so you know which direction they point. What we really microscopically mean when we have a magnet is that we have magnetic moments, spins, that are all aligned. So if we could look into that magnetic moment, if the net magnetic moment was pointing up, that would mean that all of the spins are aligned in the up direction. And indeed, if you were to take your, oh boy, fidget spinner or your bar magnet and heat above TC, put it in your microwave, the magnetization, the magnetic moment in the z direction would go to 0, where it started at something finite and positive. If we were to cool back below TC, slowly, thermodynamically, we would start with a system that has its microscopically spins disordered, no net orientation. If we cooled that system slowly, what we would find is that some of the time we generate a magnet which is pointing in the direction that it was initially. So while mz starts at 0 at above Tc, it could go to something finite and positive. However, that would only be about 50% of the time. The other 50% of the time, it would generate a magnetic moment pointing in the opposite direction. That would just be empirically what we would find. We would find that with equal likelihood, if we scramble those spins by heating the system up and then cool it back down, half the time those spins would realign and point up, and the other half the time they would realign and point down. Alternatively, if we kept the system below Tc, but manipulated the system by applying a magnetic field. So we start with our magnet freshly bought from the store, magnetic moment pointing in the up direction, so from red to white. Ooh. With net magnetic moment mz, finite and positive. If we applied a really strong field, let's call it hz, which was really, really negative, we could force the magnetic moment to realign and point down. It would be energetically favorable for the system to do so, but would require some energy to do that conversion. And if we went in to measure the magnetic moment, indeed, we'd find mz is finite and negative. However, if we turn the field off, then below Tc, we would see that that magnetic moment persists and stay pointing down. So we could take a magnet, heat it up to lose its magnetization, cool it down, and we find that with equal likelihood, the spins realign and point up or realign and point down. Alternatively, if we kept it below Tc, we could manipulate the magnet by applying a field to force it to point up, or by that matter, force it to point down. And if we turn the field back off, it would stay there, and it would stay there for a macroscopically long time. So what gives? How would all of this actually work? Well, microscopically, those spins don't know what our z direction is. The macroscopic object has some extension, some different shape in z. It's a bar longer in z than in x or y. You might imagine that that matters, but whether or not z points up or down is arbitrary. And if there is no applied field to break that symmetry, nothing in the Hamiltonian to say that z is distinct, pointing up is distinct from pointing down, all of the spins shouldn't matter if they point in an up or down position, as long as they're all doing the same thing. So the total system should have an up-down, fancy way of saying two-mode Z2 symmetry. So if I was going to look microscopically at a collection of spins, say these ones are up and down, like so. If I flip every one of those spins, those two configurations should have the exact same energy. It's just like rotating the whole system around the plane of the page by 180 degrees. That shouldn't change the energy of the system. So that should imply that those two configurations have equal weight, equal Boltzmann factors, will contribute equally to the partition function, because the partition function, after all, just depends on the energy. And yet, if they had the same weight, if up and down were equally likely, below TC, we would never have a system with a definite magnetic moment. So what gives? So to restate the argument, if those two configurations have the same weight, they should contribute equally to any expectation value. That should be the same if all of them are pointing up or all of them are pointing down, which would seem to suggest that in the absence of any fields that break that symmetry, the system should always have a zero magnetic moment. And yet that's not true. We know magnets exist. So how is it possible that the system generates a magnetic moment? It must be because that symmetry, that up-down symmetry, is spontaneously broken. It must be that while thermodynamically both cases are equally likely, that interconverting between the two takes a macroscopically long time. So that from a thermodynamic or statistical mechanics perspective, the symmetry is broken through the symmetry is broken spontaneously through the spontaneous fluctuations that the system undergoes as it cools down or as it emerges from some originally disordered state. So that is in fact the notion of symmetry and the breaking of symmetry, which becomes fundamental in a discussion of phase transitions and the statistical mechanics of those transitions. In fact, it's the enumeration and elucidation of symmetries, which gives us a framework for thinking about what phases can exist, why they exist, and how to analytically consider them, how to make sense of their properties, to uncover, for example, why universality exists. Universality and symmetry turns out to be two sides of the same coin. Okay, so that's all I've got for today. We'll delve a little more deeper into this in the next lecture, where we actually introduce some explicit models that we can start wrapping our heads around, but we'll leave that for Thursday's lecture. So I hope to see you all in the live session on Tuesday. I know you all will be, or many of you will be, fighting with a quantum midterm. So hopefully that doesn't prevent you from still coming into class. I will look forward to seeing all of your smiling faces then. All right.